Welcome back to the 2019 Operations Research Center IAP seminar. So we're going to start off the afternoon session with a panel of practitioners, both from industry and in research labs. So I'm going to go ahead and introduce the panelists. They'll each give maybe like a 10 to 15 minute spiel about what they do, and then afterwards we'll open it up for discussion and questions. So on our panel, we have Bala Chandran, who is the co-founder and CEO of Lumo, which is a Boston-based startup that forecasts flight delays. Before that, he had worked in consulting at Analytics Operations Engineering, and he has a PhD from Berkeley, where he worked on network optimization algorithms. And then we also have Virginia Goodwin, who is technical staff at Lincoln Labs. She's a member of the Homeland Protection Systems Group and the Homeland Protection and Air Traffic Control Division of Lincoln Laboratory. She joined in 2004 in the Air Missile and Maritime Defense Technology Division. Her bachelor's degree was in physics from Wellesley, and her master's in electrical engineering is from Harvard. And then finally, we have Kermit, who is a director at Wayfair. He's a director of the operations research team and leads projects to optimize warehouse efficiency, order fulfillment in North America and Europe. Before Wayfair, he also worked as a consultant at Analytics Operations Engineering and at McKinsey. He graduated from West Point and got his master's at the ORC in 2001. So we'll start off with Bala, who's going to talk about his work at Lumo, and we'll go from there.
Thanks, Kevin. Cool. So is it okay if I stand out front here? Is that good? So like Kevin mentioned, my background is in operations research. I'm an optimization guy. I just fell into machine learning by necessity. I mean, it's almost like if you want to run any sort of thing with any data, you have to learn to do some machine learning, so I learned that over time. Our company predicts flight delays, which sounds like a really cool project, which it sounds like a class project, but it's actually more complicated than you would think. The company was founded 4 years ago. My co-founder is a professor here at MIT in the Aero-Astro department. And if you think about the problem of predicting flight delays, it seems like a pure machine learning kind of play. You would throw in a bunch of features. You would say, let's correlate delays to weather, time of day, day of week, airline. You can throw in a bunch of features and say, okay, go ahead and predict this delay for me. That's kind of where we started. And it does okay. I mean, you would expect that a flight in the evening does worse than a flight in the morning, and any machine learning algorithm will pick that up. But then a lot of weird things start to happen. So today, for example, there's massive cancellations in the Chicago area, in Minneapolis, and so on. And it's because the temperatures are so low that people can't even go out and work to get the planes ready to get off the ground. And so if you've never seen that temperature in a generation, your learning algorithms aren't going to pick it up. I mean, you're going to see some weak correlation between lower temperatures, more delays, but that's a complete outlier. Right? Another example would be, we were trying to predict delays at San Juan in Puerto Rico. And for some reason, our model kept saying there were going to be terrible delays this year. And obviously, it was because much of Puerto Rico, the airport was shut down last year for Maria. And the learning algorithm said, I'm learning from history, and I can tell that Puerto Rico has a ton of cancellations. And again, so there's limitations to just applying a pure machine learning type approach. You could clean up the data. Obviously, you could clean up outliers. You could do all of that stuff. But at the end of the day, we then said, OK, what we're modeling is really a queuing network. And if you think about it, the air traffic control system is this giant queuing network. There's each runway is a server. There's entities that move from one server to another, and then they go through a certain set of tasks. So in theory, it's just a plain queuing network. So you could then say, all right, if I'm an OR person, which is where I came from, I can say, all right, I know how to model a queuing network and queuing behavior and say, all right, this is this kind of queue, it's in whatever, MD1, whatever, you can fit a queue. And so eventually where we settled on, and I'm not giving away any deep secrets, is we now have two models. And again, the context for this I should mention is, how do machine learning and traditional OR optimization kind of fit together? So we have, if you think of it, we have this one model that's kind of a top-down machine learning approach. And it says there's a 50% chance of a 2-hour delay tomorrow on this flight. And then there's a queuing model, just a bottoms-up kind of queuing model that says it's going to take you, this flight is going to take off at this time, and then it's going to arrive at the queue at this time with this distribution, and so on. And so the bottoms-up model wouldn't be confused by the issues at Puerto Rico. The model would say, okay, I see that the runway is open. I know that I can squeeze these many aircraft through per hour. This is the rate. And therefore, I'm going to go ahead and the bottoms-up model is going to say, San Juan is totally fine. There's going to be no delays. Similar, it might get thrown off by the temperatures too, because we're not modeling how cold it is for people to go out. But the philosophy of the company's models in general are, for almost anything we do, is there's a top-down machine learning approach. And then there's a bottoms-up simulation queuing type network. And we kind of reconcile the two. Over time, we've learned when to trust one over the other because they take different things into account. So, the ML model can take a ton of features into account. The simulation can only do so much just because you don't want to simulate. You want to get the right level of abstraction when you simulate things. And so when you simulate it from a bottoms-up approach, we learn certain things. When you do a top-down thing, we learn certain things. And then eventually the challenge is how do you reconcile those two, which is itself an interesting one. Another interesting problem is trying to predict. One of the reasons for delays is the cascading of delays. So a flight A to B is delayed, which causes a flight B to C and C to D and so on to be delayed. You could say, all right, I can learn that. I can learn that behavior that says, under these conditions, United is going to swap this aircraft for the other one, so it's going to mitigate that disruption and so on. So I can do a pure learning kind of approach there. But being a network optimization guy, I said, okay, let's try and think about, there's rational decisions being made when an airline swaps aircraft. So if you could say, is there a rational set of costs under which the optimal solution looks like what you're seeing? And so again, there's this top-down simulation that says, with this probability, you're going to switch this aircraft and you're going to mitigate the delay. There's a bottoms-up thing that says, if I run a matching algorithm, here's what I would do if I were rational to minimize costs. And they serve as a check and balance on each other. Right? And so I think what we've learned, not necessarily by design, we don't publish papers, but both approaches have their strengths, and they kind of serve as a check and balance on the other. And if you model both of those right, you can get the right mix, the right balance, and that's how we predict our delays. I'm happy to answer more questions later, but that's basically how I thought that might be interesting. Thank you.
All right, so today I'll be talking about some work that we have done at Lincoln Laboratory addressing using modern machine learning for some practical surveillance applications. And one problem that we're all very concerned about is the potential for disruption that small commercially available unmanned aerial systems, UAS, drones, present. And in fact, it's funny that you just spoke because one of the big incidents that just occurred at Gatwick Airport right before Christmas was they had to shut down the whole airport because there were some errant drones in the airspace. And it was a big public safety hazard. And in particular, one of the most challenging cases for these small UAS is in a cluttered urban environment where your traditional air surveillance, which is to say your radars, is impacted by the urban environment. So naturally, we turn to machine learning, to computer vision. And so just to set the scene for you, we have this example of a typical urban environment, which happens to be Beacon Street in Boston. You may recognize King's Chapel at the end of the road. So audience participation moment, although your screen resolution is really good, how many of you can see one UAV in this image? And how many of you can see two? Yeah, so there are two. Now, technically, they're photoshopped in because it's illegal to fly over pedestrians, and we didn't do that. But nonetheless, I hope this illustrates to you it's a very challenging, cluttered environment on the computer vision side of things as well. And then when you think about not just doing this for this view, but now if you're thinking from sort of a defended asset kind of perspective, say you want to protect an important building like the Massachusetts State House, and now you have to do this problem oopsie, the little red pointer doesn't go that far, there we go, all around the asset, all the streets, across the public gardens, or the Boston Common. It's a big problem, and it's a very challenging problem, and it's a very challenging environment. So this was the problem we were looking at. Fortunately, machine learning came along, GPU computing came along, so concurrent with the rise of these small UAS is the rise of this technology, and I'll discuss some things that we've done to try to address this problem. So just to lay out in words the challenges that I'm sure you've already inferred from the example, we have these urban canyons, so your long-range sensors are already occluded, and these very restricted lines of sight. So we're going to need a lot of different sensors, or a lot of small sensors. So they're going to be low cost. They've got to be off the shelf. Very short response timelines, again, because of the restricted lines of sight and because these things can pop up really quickly. So we're going to need to automate as much as possible because you can't expect a person to react that quickly necessarily. And then dense clutter of comparable size. So any sensor that you tune down to find a small UAS is going to find everything else as well, people, trucks, cars, etc. So of course, unsurprisingly, in this day and age, we're going to exploit novel machine learning techniques to reject all the non-UAS targets that we find. So the architecture that we have proposed, and that is actually currently being prototyped and deployed, is a two-parter. Below the rooftops, when you're in these urban canyons, we propose a network of cheap, commercially available cameras with a smarter machine learning back end. And then when you go above rooftop, and I'll talk about this second half, you can bring back in a longer range sensor like a radar and see what performance you can buy back with that and doing some intelligent things with your machine learning. So I will start talking about in the below rooftop case when we're just focused on having cameras, and then I can talk about what we can bring back with your radars and summarize. So this project actually started in spring of 2017 when my group leader came to me and my office mate and said, hey, we have this problem, we're looking at solutions, what can you give us in the computer vision domain? And we said, buddy, you are in luck because we are in a good place right now. In 2017, I should explain this chart first, I guess. Where's there he is, no, there he is. So you may be familiar with this kind of layout where you have your mean average precision of your classification on the y-axis. You have your processing speed on the x-axis in hertz. So because we were intending to work with full motion video, we wanted to be at 30 hertz or faster processing speed. And we, back of the envelope, calculated that if you wanted to generate a pretty reliable track, we would need about a 50% mean average precision on our UAS detection on a per frame basis to get enough detections to build a reliable track. And that was a high level back of the envelope calculation, but it gave us a place to start with. So this was the lay of the land of your algorithm performance in spring 2017 when we started this. And the orange dots were sort of the pre-neural net algorithms, these deformable parts models, which were still really good for their time. And I have implemented those, and I have deployed systems with those, but they still weren't meeting the performance requirements that we really wanted. And then the first generation of neural nets came out, the RCNNs, fast RCNNs, faster RCNNs, those green dots, and that was great, that was amazing. You know, all of a sudden, boy, your computer vision performance just skyrocketed. Amazing, but still a little slow for full motion video. And then that next generation of algorithms came out, the blue dots, which are your YOLOs and SSDs. And this was the state of the art when, spring 2017, my group leader said, what can you do for us? And we said, we're ready. So we picked, so 13 through 17 are all YOLO V2. And then there's SSD right on the edge, 9 and 10. And YOLO V1 is 11 and 12. So at that time, we picked YOLO V2, high res, and we just threw our data at it. We took our UAS data that we had collected in the field, and we also used the COCO small data set just so that other people could compare as a publicly available data set. And we just threw them into the algorithm. And unsurprisingly, the performance plummeted well below what we would need for our system. And this isn't a shock. It was stated in the paper. They knew it didn't perform as well on small targets. And if you take a look at the type of typical surveillance data that we were collecting in the field of our small UAS and compare that to the data that it's trained on and that its performance is based on, it's pretty obvious what the difference is. You know, we have such low resolution data that it's a real challenge. So we looked at that and said, all right, what can we do to buy back the performance that we need? So now I'll just step through the steps that we took. So on the top is a high-level diagram of the YOLO V2 algorithm. And then on the bottom half is our algorithm, and I'll step through the steps. So first thing, big thing, is that we took an idea that had been published with the SSD algorithm of doing a high-resolution detection layer, just whipping those features out at the higher resolution level and applying the exact same detection layer at a higher resolution. And that buys back some of your performance on your smaller targets. You'll also note that we started with slightly higher resolution imagery on the input, or larger size imagery. We took out one max pool layer, again, to preserve, you know, the number of pixels we had, because our really small, low number of pixel targets we would just lose over the course of these convolution and max pool layers. And then the other thing we did was that rather than learn from the training data some kind of k-means clustering of what our bounding box priors should be, we simply scraped the web for published UAV sizes and translated that into our appropriate bounding box priors. So with those improvements, we were able to buy back sufficient performance on the algorithm to get us to where we needed to be for the system. And we also traded off some processing speed. And that was actually, I didn't point it out in the overall chart, but there is a trade-off of, you know, performance and processing speed, unsurprisingly. So that's great. And just as an example, I have a video that we took of our, on the top you'll see the unmodified YOLO network on a video that we collected, and the bottom is ours. And these are, is it playing? It's not playing. Now it's playing. And these are purely the detections. We haven't put them together with a track yet. But you can see that we're getting more detections and we're getting them earlier. So we're going to do a lot better job once we put that, it's going to come back across in a second, once we put that together with the tracking algorithm. So that's the kind of performance improvement we got, which was great. That was enough to be going forward with and rolling out our system. So then the next piece was now, you know, okay, so we have something for below rooftop. Now if we go above rooftop, what can we buy back? So the concept there is, well, we can bring back our radar because we're not just running into buildings all over the place. We can look up into the blue sky. So we can get our longer range detections. But we're still going to get a ton of clutter because we're going to see so much stuff with the radar. So what we really need is a clutter rejector. So we thought, okay, pair the radar with a camera and put the two of them together. And as a bonus, with the radar's error are within the camera field of view. So we can use the radar detections to localize within the camera imagery. So again, on the bottom is the exact same machine learning network that I just showed you for the camera. And then what we did was we took our radar data and we rotated it and flattened it so that it was in the appropriate corresponding field of view as the camera. had to learn a debiasing layer, because of course there's a bias between the radar sensor and the camera, and a decimation layer, and then we just bring those radar detections as features into our network. And the other thing we do is we can use the position data from the radar detections as a positional prior within our image field of view. So in the same way that we're using the bounding box priors, now we're giving it a positional prior, which is really helpful because you're taking the whole image and you're saying you don't have to look at the whole image, just look at this part of the image. So with that addition, and this is just for blue sky, this is not, again, below rooftop, we got a big performance improvement because, again, you're really giving it a much smaller area to interrogate and saying, look here, and you have these additional features. So that was a great improvement for our above rooftop domain. So we're continuing to move forward with that system. And so in summary, I hope I've convinced you that the small UAS detection in the city is challenging. You know, we've modified our deep learning algorithm to get pretty decent performance. When we bring back in the radar, we can get some really interesting performance with a pretty straightforward fusion mechanism. And we've demonstrated this on our sort of development system. We're working forward to a deployment system right now. And going forward, of course, we mostly just want to keep collecting more data. And there's a lot of interesting opportunities in multimodal, so IR as well as EO. And there's, you know, we've collected like a tiny amount of data in the grand scheme of things. We would always like more data, different backgrounds, different weather conditions. All of these things are going to affect performance. So it's a big data collection effort. Obviously, we're continuing to look at new algorithms as they come out. And the other interesting thing that we're working forward is using synthetic data because, of course, collecting data is very expensive and time-consuming, hard to do. And we'd really like to augment our real-world data with realistic synthetic data. Particularly, you know, you got to set up a whole system, and you can only get certain angles on your UAVs, you know, which may not be representative of any possible crazy scenario you may see. We could really do that with synthetic data. You know, we could generate any scenario you could imagine. So we'd really like to get that going. And I think that's all I've got, except the acknowledgement to my coworkers. And I guess I will take questions at the end. Okay, thanks.
So I'm going to start off just by giving everybody a warning. This thing is all over the place. I actually don't do much machine learning in my current position, which is relatively new. I just started working at Wayfair back in May of 2018. So I figured what I could do is kind of just talk about my experiences and what I've seen so far, things that work, things that don't. Having kind of doing consulting for 17 years before I joined Wayfair, I've seen a lot of things that people have tried to do and situations that kind of came up. So I just kind of want to do a survey of my thoughts on machine learning and its appropriate use and what people try to do kind of out in the industry. So at Wayfair, I'm on the OR team. We actually do more optimization. I'll go into a couple of little machine learning things that we kind of do there. But if you think about it as a website with an operational back end, there are lots of applications that various groups are using. There actually is a parallel team to ours, the data science team, that does all the things that are kind of on the board. There's an image recognition thing. We're trying to invest a lot in, you know, having kind of augmented reality and being able to put a chair in a room. But not only that, but to say, oh, if you see a chair, take a picture of it so you can see what it looks like and then come up with other chairs that are similar to it. We have a group that's focused on pricing and kind of doing some personalization aspects of pricing. What are situations where we can give somebody a higher price or we can give somebody a lower price? Search is just a big general element for it. And then marketing is kind of a big category, but in terms of email offers, just even who we spend campaign dollars on, there's a lot of machine learning going there. And for instance, as an employee, kind of the price doesn't quite matter. One of the benefits that we get is we get this employee discount where we pay the cost of the item, the Wayfair, plus some small upcharge percentage. But this stuff does work because I put on my cart that I wanted to buy a Roomba, and I didn't buy it because I just didn't feel like it at the time. I just kind of looked and tried to see what the employee discount was and what the price was. And I got maybe 6 or 7 emails in the next 3 weeks saying, hey, you got a Roomba, we'll give you another $5 off this thing, you know. So these kind of things do work, and we have teams kind of working on those. But I kind of wanted to talk about, just in my kind of consulting career, kind of situations where either I was put on a project erringly, or people have asked us to do some work. And these were situations where I don't think it was appropriate. Now, this is a couple of years ago. Maybe you can argue that some of the new techniques or more computing power might get you there, but I think in most cases this might be more or less universal. So one thing that I always dreaded when it came up in a consulting context is what I would label general insights. So it's one of these things where a company says, hey, we got lots of data. We're just going to give it to you, and you got to figure out something that we can make money off of, just out of the blue. Yeah, I mean, there's nothing wrong with kind of using more advanced techniques to look at data where nobody's looking at it and see if you can find something. But one of these things that happen in consulting is people are paying you money to do it, and there's some expectation that you're going to deliver something. So one of the issues with general insights is you never quite know what you're going to get, and I would say it's like rolling the dice. And in my experience, it's probably about the same odds as blackjack or craps. You know, it's about 50-50. And when people pay money for you to do something, or you make a promise that, yes, I'm going to figure out some way to save you money, that's kind of a scary prospect. Other thing that comes up is rare events. There was an example of a project that actually was done, and somebody attempted machine learning on it. Wasn't really the right thing, where the situation was there was a railroad company, and they have a rail yard, and they have to move trains around, and trains go back and forth on this rail yard. So they wanted to predict what set of circumstances would kind of create what they deemed a catastrophic failure of this rail yard, where it was so congested you were pretty much in gridlock, and you had to do emergency efforts to unravel the trains. And they decided to use machine learning for this, which, I mean, to put things in perspective, this has happened 3 times in the past 25 years. And I mean, if you really think about it, and you think about the factors, yeah, weather is involved, and you can figure out all these other things. But this kind of goes to what Bala was saying, which probably drove his methods for his company, where just even some basic queuing models or looking at the physics of the problem, especially in this situation, is probably more appropriate. So in general, if things don't happen very often, or they happen once a decade, it's probably not a good idea to do machine learning to try to figure it out. Another thing that came up a few times, it's on the bottom of the slide, is I actually had somebody call us up and say, hey, we want your help, and we want to use this new machine learning stuff to figure out prices. And I was like, well, what kind of prices? And they wanted to try to measure ocean container prices, you know, through various lanes across the world, because they wanted to use that information to negotiate for 4- and 5-year contracts and make differences in the spot market. Well, I kind of told them, if I could do this project for you, I wouldn't give it to you. I would use it myself and arbitrage this thing and be a gazillionaire. I mean, there's some things, especially when you're talking about long-term effects of a market, where it's, you might get some result, but it's probably going to be a false result. There's still this notion that markets are relatively random. You can't really track them over time. And if anybody did, you would know who that person was, because they'd be flying in fancy jets and have a mansion that goes all the way up to the sky. So that's something where people get this notion that machine learning is the greatest thing ever, it can do all this stuff, and people ultimately go there. Now, I'll make a distinction between that and a lot of like trading that goes on in hedge funds. When you're looking at a very narrow time window, there are correlations and things that you can do to take advantage of the market, but those types of models don't hold positions for very long. We're talking minute by minute, but from a contractual or operational standpoint, it's probably a scary thing to try to approach. And then diagnostics is another thing. I mean, in the little picture, there's a guy hooking up a computer to a car. Those computers don't use machine learning models typically. It's kind of built in the engineering specs of the car where they have tolerances and they figure things out and it's just measuring those and they have specific sensors in places. There are some opportunities to just read a bunch of sensors and make some assumptions of what's wrong with the piece of equipment. And I'll talk in a little bit more detail about an attempt to do it. And I see Ted here, he worked on this briefly. And I kind of took it over and tried to operationalize it. So we had a situation, this is still in consulting days, where there was a company that serviced CT machines. So these are the CT machines you get imaging at the hospital. They're very expensive. Hospitals usually only have a couple of them. And if they happen to go down, it creates serious problems with the schedule because they have to cancel a bunch of appointments. Some of these things are for emergency use, like a trauma patient comes in and they have a gunshot wound, they need to figure out what's going on with them. They have to rapidly put them in these things. So it's important to keep good runtime. And the service company has some promises that if something goes down, they'll fix it relatively quickly. And they charge kind of a yearly contractual rate. And then whenever these things have an issue, they'll take care of them. So one of the issues is these machines are kind of complicated. And it's a situation where somebody will just call you up on the phone and say, hey, my CT machine's broken. It's not moving. And there's a crew on the phone that can go online, kind of look at different logs in the machine, try to figure out what's going on. Sometimes they can fix it remotely and reboot it. Other times they have to actually send somebody on the scene to look into it and repair it. And a lot of times this process of figuring out what's wrong with it takes a long time. And even worse, you show up thinking that something is wrong and you have parts, replacement parts for it. And then you start getting in there and you find out, well, your replacement parts aren't going to work. So you have to come back the next day. So it becomes an expensive prospect. So one of the things we're tasked with is coming up with a machine learning model that may be able to diagnose the problems with the machine. We have two sources of data for this. We had a kind of basically what the customer said was the problem, symptom data. It's kind of free text in the customer relational management system. And then we have this log data that machine generates. So we created kind of two separate machine learning models to handle both, and then we convolved them to get kind of a final answer. And through a lot of digging and questioning and research, we figured out that there are probably like 120 possible things that could go wrong with the machine, and those were kind of our classes that we were trying to predict. Ultimately, what we ended up doing is creating a tool for these diagnostic people out in the field to use that would read this log data from the machine, that would take their customer data they put in, and would give out 3 recommendations of what the problem would be. And the idea was these 3 recommendations would speed up the troubleshooting. This didn't work out so great, if I have to say. Like, we built the system. I would pat myself on the back, because early on it was much worse, and we got to this point where the top 3 recommendations were right a good portion of the time. But there are a lot of issues in terms of you have these grizzled CT veterans that are on the phone taking these calls that know the machines pretty well and can have this intrinsic knowledge. So they didn't quite trust the data that was coming out of this thing, and they were expecting it to be more right than they were, and it wasn't. And the other issue was just the classification. The way we defined it, we achieved this particular amount of being right in top 3 recommendations 80% of the time. But actually defining what the actual solution was for classifiers was a little bit nebulous. So, and the way we framed the problem, we were right most of the time. But we weren't actually right most of the time because we had to do free text in the data to figure out what ultimately to even train the model on, and we'd have to go parse through it. And there was enough error in that whole process where it probably generated more error in our system. So it just became something that was barely usable. And it's great. I think it was more for marketing purposes for the company to say, yeah, we use these advanced techniques and they can sell it to their clients. But in terms of actually taking something and being able to make it revolutionary or like a big kind of step change in the business, we weren't really able to accomplish it. And if the machines have been designed to actually output logs that were for this purpose, if maybe this system was cleaned up so you can actually have these 120 things that go wrong so somebody can code it directly without text recognition. There are a lot of things that could be done to improve it, but I think, long story short, these things aren't easy, and it's not the algorithm that's the reason that it's not easy. It's a bunch of other factors. And then one thing that we are looking at now, at Wayfair, I am working on warehouse optimization. So simple things like getting people to move boxes around more efficiently. And one of the first projects we're doing is pick path optimization. So you have a set of orders in the warehouse that all need to be picked by people. People are driving around equipment called order pickers. They go up and down. They have a big platform behind them. Can fit, with our box sizes, something between 5 and 20 boxes. At any given time, there's more to grab than there are people to grab it or order pickers to grab it. So the idea is, how do we establish tours for people to go on to pick up things to drop off at the conveyor that goes out to the trucks in the most optimal way? And the nice thing as we research the problem is this isn't a traveling salesman problem. Like if I generate a path where somebody has to pick 15 items, it's going to fill their equipment. Just the dimensions and the way the warehouse is structured is a rectangular structure with aisles and columns and cross aisles. There's actually some dynamic programming algorithms that run in linear time that you can use to figure out what's the distance between a series of points. And that's really efficient and it's great. The real trick in the NP hard portion of this problem is figuring out what tours to create. You have all these different things that people can pick up. So batching the orders in an efficient way is the hard part. And to do that, you need to be able to evaluate what does a batch mean? What's the score of a batch? And you need the distance for it. So one thing we're doing is, even though the routing algorithm is great, it's a lot more efficient than the traveling salesman problem. It still takes a little bit of time. And if you want to do a lot of iterations in this batching algorithm that's calling it constantly, then you want to make that as fast as possible. So one thing we're looking into, and I think this is a general optimization technique, a colleague of mine is also doing this for manufacturing transfer lines and their performance, is a machine learning approximation for your optimization. It's have this optimal routing structure generate a bunch of kind of false routes in different situations, feed a machine learning model that would be able to take in the inputs of this batching algorithm and return a distance or predicted distance. In papers we've read, they've been able to do this with like 97, 95% accuracy. And that way, we can just get the gears going a little bit faster in this model. Just real quick, I wanted to finish with a couple of other random things. They actually, in terms of choosing models and what to do, another thing that's always come up is, back to the insight question. Sometimes your choice of model isn't going to be what gives you the best prediction. It's what gives you the best knowledge on kind of what some of the factors are. And there are actually tools out there. It's one that worked on at McKinsey that came out that does a pretty fancy job of this. It almost kind of automates the person, some of the things that back in the day we used to do where you tried to figure out what kind of adjustments you're going to do to your variables and how you're going to change your covariates and do transformations. There are actually tools out there that will take something and do hundreds or thousands of different combinations or transformations on something and automatically feed it into a machine learning algorithm for you to, so you don't actually have to create these factors yourself. So I think that's kind of a new movement in terms of some of the tools that are out there. You can still fall into the same traps. We had access to this thing, and projects went a lot faster, but still, you got to the point where people make mistakes or the data wasn't great, but it's still one of these situations where not only are the algorithms getting better and faster, but some of the tools that wrap around the algorithms could get better and faster. And with that, done.
So thanks to all of you for talking about your work and your opinions on machine learning and operations research. We're going to move on to the more Q&A discussion part of the panel. And to start that off, I have a few questions that we asked people to submit from earlier that I'll just start off with, and then we'll open it up to the audience for other questions. So to start off, because our topic is machine learning and operations research, how do you feel like your respective fields have adapted or changed as ML research has advanced, both in terms of progress it's made and how that's created new difficulties? And just whoever wants to go.
So, ML has almost become a tool that is as basic as math and most things like that. It's hard to do. Whoops, sorry. At least in the stuff that we're doing, machine learning is sort of a given. I mean, I guess it's, if you had to estimate a distribution, you could do it with stats, but then there's just so much more data, there's just better techniques. It's almost, the reason we do machine learning is because it's become so easy to do it. And you almost don't have to know how things underneath work. You can throw a bunch of things into some ensemble modeling, you'll get something pretty decent at the other end. So the danger with that is there's a lot of people using machine learning without really knowing how it works, and you have to be careful. So, you know, when I go out and I talk to airlines, they might say, well, do you guys do AI? And it's kind of a yes and no. I mean, the marketing side of me says yes, but the engineer in me says, oh, if you want me to say yes, I'll say yes. So it's, the problem is most people out there in the industry don't know what machine learning is other than self-driving cars or something that they've got in their heads. So I think as a community, my biggest struggle is internally we know what it is, but explaining it to customers, telling it what it can't do is the biggest challenge we face.
Take a crack at that. So in our domain, the state of computer vision now has opened up a whole set of problems that we couldn't really solve before in terms of automation that we're now able to do such a better job on, like what I showed there in terms of computer vision and picking out these targets and getting closer to sort of human level vision quality. So there's a whole category of problems that we can do a much better job on, which is great. And exactly what you say, we have a lot of problems with people. In the past 5 years, the people, our sponsors, have gone from, oh, what is this? I don't know, to, so you're doing machine learning, right? You know, they've totally got on board with AI, but they don't even necessarily know what they're asking for or what's possible. So there's a lot of education going on. And the other challenge is trust with the algorithms. So in our cases, we're always going to have an operator. We're always going to have a human in the loop. And if our algorithm gives a bad answer and the operator doesn't trust it anymore, if it gives too many bad answers and they just turn it off because it's bothering them, that's going to be a big problem. So we're going to have a big challenge going forward with demonstrating reliability and building trust with the operator community. And I think that's going to be a big one in the next many years as machine learning algorithms become part of more people's everyday life, certainly for us.
Yeah, it kind of gets to one of those things that, why I was saying, these situations that kind of come up. The funny thing is, just when you talk about regular optimization and those kind of things, I find it harder to convince like executives that that's a worthy thing to do. But you say, oh, we're going to do some machine learning algorithm, and all of a sudden their eyes perk up and their ears perk up and they're ready to deal with you. But it gets down to, there's a lot of buzz out there in the world, and everybody thinks it can solve every problem, and it's the greatest thing, and if you're not doing it, then you're on the back of the bus or not even on the bus. And that's kind of the business speak. But it really does come down to the operators themselves, and the operators aren't in the boardroom reading all these Newsweek articles or something. They just want something that works. So you find yourself in positions where you have senior people asking for things that might not be appropriate, or even if they are appropriate, the devil's in the details and being able to actually implement these things. So I think that's a challenge. And the other challenge is also just thinking about it as not the only tool. I think in a lot of cases, people pull it out of their pocket and it's an ML kind of Swiss Army knife just with different ML techniques. But remember, there's everything else that we learn while we're here, and kind of having an approach where you integrate all of them is probably a good one.
Great. I guess kind of continuing on that track, do you feel like your position within your field, you're constantly kind of like not like a naysayer, but like, hold on, take a step back, let's think about this in a different way? Or do you feel like there's also other people kind of serving that purpose who are just not necessarily dragging or like pushing the newest thing all the time?
So I got the microphone, so I answer. I feel like if you take the approach that if you come up with a problem or a problem is presented to you, if you have the time, spending the time to do a little bit of research and figure out what are all the different ways that you can go about it, understanding the toolkit that you're used to and new techniques that are out there, I think that's okay, as long as you're willing to take a deep breath and try to figure out and do things the best way possible. But trying to just do something for something's sake, like machine learning, just because everybody thinks it's great, is a different story. So I don't know if you necessarily have to be a naysayer. And at the end of the day, I mean, how many OR groups are there in companies? How many people actually do this sort of thing? I find it rare, at least in the company world. Consulting's a whole different story because you got to deal with those people in the boardrooms, where somebody will come to me and say, you have to do it this way. They just present me with a problem, and it's kind of up to us to kind of figure out the best way to do it. Now, do I personally start rolling my eyes sometimes when I hear some of these things? Yeah, but maybe I deserve an attitude adjustment myself, so.
Well, as I alluded to, we've gone through sort of the span of from 5 years ago, we're the ones saying, no, we could really do this, trust us, this is going to be great, to now being like, okay, slow your roll, machine learning doesn't solve every problem, yeah, we're going to use AI, So it's been the whole spectrum. But fortunately, in our role at the lab, part of our mandate is to educate our government sponsors on what's reasonable, what's feasible. So when somebody from industry is trying to sell them this thing and it's got this beautiful sheet and it's all glossy and it's going to solve all their problems, our actual mandated role is to come in and figure out how much of that is really going to work and how much is a little too much salesmanship. So that's a good place to be, you know, so that's part of what we do.
Yeah, what they said. And I think all of us who, I have a PhD, and I can tell that when that same message comes from someone at MIT or someone who has a PhD who has done this, it gets taken seriously. And even if there's an investor who says, I really want to know your opinion, and I can say, no, look, I know this stuff, and this will work and this won't, it carries a lot of weight. So don't underestimate that weight that folks have at people. If you're at MIT and just say, look, I know this stuff, people take you seriously. And people are willing to be educated, because the only other source of information that they're getting is from the news, from sales folks, and so they're willing to listen. So it's okay to spend 5 minutes educating people without talking down to them, and most people are willing to listen.
Cool. How do you see the working relationship between like academic researchers or more like people publishing papers and practitioners in your particular domain? Like, are there large differences in considerations and goals that you see, and like how do you expect to deal with that?
Oh, I can hit that one, yeah. So again, as I alluded to in my talk, a lot of what's getting published and a lot of what's going on in academia is currently touching on these very nice, highly curated data sets. And then when you go into a system that's going to operate in the real world, your data is not going to be like that. So that's a big difference. Now, I will say that the academic publishing, everyone in academia is coming into that. They realize that these data sets, while they've been amazing for the development of the field, they're not the end-all be-all. So they're moving in that direction. But that's the real biggie, is the difference between like, oh, look, I get an amazing result on ImageNet, check. Go to NIPS, go to ICLR, whatever. And then I want to use that algorithm, and it's like, oh, not really for the real world.
Yeah, I actually think but still for machine learning or data science, it's better. So we're thinking in our little operations research team at Wayfair of kind of setting up some sort of partnerships with academia to do research on some of the problems that we have. And one of our struggles with it, besides being a small team and trying to manage it, is the fact that you kind of need to have some deep operational knowledge to build something that's going to work. Like, you need to know how our supply chain works and some of the issues or constraints that we have in a decent amount of detail. So kind of managing that and doing it in a quick period of time is kind of difficult from that standpoint. However, our data science counterparts actually have quite a few of these arrangements, because they can say, hey, here's some of our data, here's some of our computer vision stuff, we want you to work on various aspects of this. So that partnership is a little bit easier, because it's easier to kind of hand that off and have people look at it or try different approaches without having to put your hard hat on and actually get in a warehouse and figure out how those things work. So from that respect, I would almost say probably it's better than traditional OR. Plus, their cycle in terms of figuring things out and getting papers is a lot more rapid. Like my warehouse TSP algorithm originated in 1981. We're doing a follow-on that came out in 1999, but so I think if anything, it enhances at least what the normal kind of field experience is between industry and academia.
Yeah, and to piggyback on what Kermit said, so a lot of OR research is about what's mathematically tractable, and most things aren't. A lot of things aren't when you try and actually go and implement them. And what the difference I've seen is we do read machine learning papers on weather delay predictions and so on, and they're fairly easy to follow. It's usually some module in R that you can use, or Python or whatever, and they exist, and you can implement them, and you can move pretty quickly. It's harder to use the stuff that comes out of OR academia, because it's slightly more contrived in what it's trying to do. And so I think that might be changing, but that's what we've seen is the OR, the pure OR. If I go to and pick a paper out of OR, it's this very specific kind of queue with this specific arrival process and this thing, and it doesn't really work. But I could go and pick almost any machine learning paper and get something out of it. So.
Okay. Are there any questions in the audience? Jessica, do you mind?
Hi, I think this question is mostly for Bala Chandran and maybe also Virginia Goodwin. How do you deal with anomaly detection? How do you decide on which data to trust your neural network and on which data not to trust your neural network?
So for us, it's when one of the models, the machine learning model, is saying something wildly different from our bottoms-up simulation. We know we're going to need to go look at it, and so that's basically how we do it. The other thing is, all of us come from an air traffic control modeling background, and so when something doesn't look right, we kind of know what it is. Just because I can look at the data and say, well, Minneapolis is it's a hub for Delta, and therefore Delta behaves differently from United at Minneapolis. But yeah, it's mostly knowing just domain knowledge, plus the reason we have that bottoms-up simulation is to call out weirdnesses in the other models.
I don't have a lot to add. The data we work with is all labeled highly curated that we've collected. So we're not really dealing with the sort of vast multi-stream data yet. Maybe we'll get there going forward, but we're not there yet.
I guess your case would be mostly adversarial cases. Like, for example, if there's a drone flying with a dog skin on it, and it's a dog in the air, and your computer vision fails.
Yes, so that is definitely a problem. We're so
Lots of dog skin drones.
so the advanced threat is definitely a concern, but we're so far from that right now. We're trying to get something for the common threat, and even I say the common threat, it is still a rare event. And we're just trying to get to that first step right now. We have looked at some of the adversarial learning to counter computer vision, to counter trained computer vision algorithms, and we've kind of looked at it like, oh yes, that exists, we should definitely get to that, but we're not there yet. We're just trying to roll out something.
Thank you. Yeah, so were there cases where, like, concrete examples where, like, either your boss or your client, you present your client or your boss like an algorithm that works, so the metric says it works, but the interpretability of it makes that the client rejects the solution because, I mean, it's the case in healthcare that, like, the doctors will not use, like, neural networks because it's not interpretable. However, the performance and the metrics are all very positive. So how do you deal with this kind of, like, dual vision of, like, interpretability and performance on the other hand? I guess it depends on the application. Maybe, like, for the detection of the drones, the interpretability is, like, as you're using computer vision, is, like, maybe less important. But I mean, the convolution is important. Makes sense. But maybe, like, for the flight predictions or for Kermit, in some of your cases, when you mentioned for the medical project, the guys in the end, they didn't want to use the solution. However, it was somehow performing well. So yeah, just if you can share your experience in each project with this.
Yeah, so it was really interesting because when we initially put out our predictions, we would say there's a 50% chance of a delay. And as a traveler, if I see that, okay, I get it, but if I don't know why, it's that much harder to deal with. And so, in fact, that bottoms-up simulation will tell you, is it because of the constraint at this node, or is it because the incoming flight is late and so on. So we use the bottoms-up thing to give reasons, and the top-down to sort of quantify. And so when we issue our prediction, we say there's a 50% chance of being delayed, and it's mostly going to be because your inbound flight from LaGuardia is going to be late. And that all of a sudden makes that data that much more palatable.
So this is a broader problem. It's not just a machine learning problem. You even find it a lot in optimization because, it comes up with an answer a lot of times. Somebody who is doing it in their head can't follow all the different iterations. So I think there are two ways to deal with it. And by the way, doctors, I feel like I find anything that you ever try to do, if it involves doctors, it's really hard. And no matter how many reasons you come up with or how well something performs, getting them kind of out of their normal comfort zone is a challenge no matter what. So that's a particularly hard case, I think. I think this whole process of just, even on a case-by-case basis, if you can't explain what's going on, because a lot of times it's impossible, at least kind of describing the methodology behind it in simple terms, which can also be hard to do, but to do that with the operators, to run relatively realistic simulations in advance and say, hey, we're doing this, we get it right 75% of the time, otherwise you get it right 55% of the time, this is what it means overall for your decisions or money. Like setting up higher level management for that sort of thing, explaining the methodology to people that are actually the operators is probably the best way to deal with it. I find that a lot of times if we're called to build something, it's not something somebody can do in their head. So you're really almost never going to be in a position where it's going to be clean and simple to say, oh yeah, well, we're doing this because of this. It's more complicated than that. So it's just a general skill that I think if you're an OR practitioner, you have to develop. And it's not always 100% guaranteed one way or the other, but it helps.
So as you say, we don't have as much the interpretability problem because a lot of our systems expect an operator in the loop, and they're going to look at the video, and they're going to also confirm, oh yeah, that's a UAV, or oh yeah, that's a bird. What we have is a reliability issue. So if it throws too many false alarms, they're going to turn it off. So what we need to achieve is just really strong reliability that they don't even have to waste a lot of time with either false alarms or, God forbid, misdetections. And that's what we need to achieve.
I actually had a question. So more specifically to Kermit, you talked about how when you were consulting, you would have general issues come up. What would you do when you were assigned to one of those problems and you couldn't say no?
Well, yeah, you just try your best. And you feel really nervous all the time. Yeah, I think it was different. So most of my time was with a small firm. We would turn certain things down. Or if it was one of those general insights, it was a situation where there were no promises. It was almost like we'd do it for free, and if we found something, then that would be an opportunity to get like a real project with somebody. That, I think, changed when you get to some of the bigger firms. And then there's that kind of wrestling of the people selling the things don't necessarily understand machine learning and the things that we do the way we understand it. So that was kind of a prime place where the conflict that was in the question earlier kind of came up. But I think that's more in a consulting context or kind of a big boardroom context. Like right now, I don't working for an actual company for the first time in my life, but it hasn't really been an issue.
I've maybe like a couple more questions just to wrap things up, and then we'll see if anybody else still has questions. So if you were to kind of speculate or get speculative, what sorts of changes do you see, like a huge influx of data in the next couple years, or advances in machine learning affecting your field? Like, you can go like 5 years out, or I mean, if you want to go like 20 years out, like how is that going to change what you do? Just take a stab at it.
I'll take a stab at it. So it's going to be hard, I think, to keep up. Just this kind of notion of, yeah, when you're presented with a problem, if you have the time, research it and try to figure all the different ways, probably won't work for me. Like, I'm talking personally. But I am kind of excited about it because there are a lot of things that, from a machine learning point of view, that I would like to take advantage of, and I think it would be better for the world. So if we get to the point where we can compute things really fast and really have autonomous cars and all these kind of things, I think just from a personal standpoint, it would be good. For a professional one, I personally just have a fear of keeping up with everything. I mean, even if you kind of focus, and again, I'm not even doing it anymore, or just little pieces here or there, but if you kind of focus in one area, then without trying to keep your eyes open, there'll be all these advances in some other place that you hadn't thought about. And then when you lift your head up, you're like, oh my goodness, how do I keep up, or what do I need to do? So I think it's even something that I've even tried to internalize, like what are things being kind of out working for a company that I can do to try to stay current, at least so I know enough to know what I don't know and what I should know and what should be going on. But I also think it would be really nice just to get in my car and kind of sleep and have it take me someplace where I want to go and that kind of thing. That's my dream anyway.
I second all of that. I'm so ready for autonomous vehicles. I think everything you said, and I was saying this over lunch, 5 years ago, neural nets weren't really a thing, except maybe if you were Jan LeCun or Alex Krizhevsky, who were building like the first ones of this generation. So I think we're going to plateau for a little bit. Everybody's making hay off the current regime. I hope that there's going to be some other crazy paradigm shifting thing coming up. I have no idea what it's going to be. Keeping up with the research and what's coming out of academia is going to be challenging. The pace is crazy. And I really think the explosion of data, and also with autonomous vehicles, I'm really hoping for smarter infrastructure to enable that. But then that's a whole new world of data. So there could be some crazy cool stuff coming out if you start building like small sensors into your infrastructure and then getting the data from that. And I hesitate to even speculate on what we'll be able to do with that kind of data, but I think it's going to be cool in the same way that the databases, the ImageNet and everything really enabled a lot of this machine learning advancement. And I selfishly want it because I'm ready for autonomous vehicles to be part of my life as well.
So for me, I think in the next few years, so we've been on, all of our stuff runs on Amazon infrastructure. And so, it used to be that if you had to stand up a database, you would have to go find a sysadmin. Today, I can stand up a database, do all of that stuff with almost no knowledge of how computers work in the back end. Machine learning is now almost there within the Amazon world, where you can throw in some data set. You can say, well, go throw these 50 algorithms at it, unlimited computing, and I'll get something on the outside, on the other side. And so it's becoming extremely commoditized in a way, and maybe that's a good thing. I mean, if you're a random researcher somewhere, not necessarily a deep machine learning person, but you have an interesting data set that you're trying to get some insights out of, where you're trying to predict something, it's going to become much easier for that person to do it, as easy as working with an Excel spreadsheet. I do think in the next 5 years, stuff will be easily usable with very little prior knowledge. But with that comes, with great power comes great responsibility. I mean, you're going to find a lot of people using machine learning algorithms coming up with outcomes that may not make sense. They may be biased. I mean, there's social applications where if you really don't use it properly, you can end up with really biased outcomes. So that I think it's going to become much more widely used, and we're going to be much more accepting. And I think the output of those algorithms isn't going to be as trustworthy as it is today. And I think that might be an interesting thing for society to work on.
Are there any other questions we want to ask the panelists? Okay, in that case, let's thank our panelists again, and we'll take a short break before the next talk at 3.